What up, guys, and welcome to week 4 of CS-330. Now, last time what we did is we we drew our first triangle. What did we do last week? Let me just double check. Oh, fudge, I have it on my other drive. Last week what we did is we built a abstracted version of a mesh class so that we can create as many meshes as we want. We enabled depth buffering in our project so we can properly get depth inside our scenes. And we also briefly went over the projection matrix, the view matrix, and the model matrix, which positions objects in the scene and also gives you your camera view, right? What we're going to do this week is we're going to flesh out our camera system so that we can, we're going to build a camera system generally from scratch. It's not going to be overly complicated, that you're going to be able to control through your mouse and keyboard. And we're also going to, what else are we going to do? There was something else that we need to do. I'm going to show you the difference between how to create a perspective and an orthographic camera. So with that said, we're just going to jump right in, get this done. It's going to be interesting. I'm going to be using/reusing some of the code provided in the Module 4 tutorial this week because it's pretty basic code, but we're going to abstract it out. Now the course, I believe, I don't know if it's this week or next week or when they do it, they provide a camera.h file, which is basically a class that's built for you that you can get off of learnopengl.com. You could use that one directly, but I'm gonna build a probably simpler version of that will meet the requirements. Always double check to make sure I'm giving you all the information you actually need, but that will meet the requirements of the assignment, but you'll understand what's going on. So with that said, let's get right into it. So where we were, so the thing that we're worried about this week is the camera, right? And we know if we go to our draw scene that the camera is pretty much these two lines here, right? This is our camera in the scene right now. So we'll just comment that for now, camera. So this is our camera. Now we want to be able to control our camera, and we're going to abstract things out immediately this time rather than build it all inline and then abstract it out later. So we're going to put these into its own class for now, and we're going to access it, and that will be our first step of abstraction. So we're going to make a class. We're going to call it camera. It's going to be in our camera.h and camera.cpp. As always, move the cpp file into your source directory. And then if you're using CMake, reload your project. If you're using Visual Studio, just make sure. So if you're using Visual Studio at this point, you're not maintaining a CMake project, you're probably organizing things a little bit differently, which is okay. I'm giving you theory and how I like to do things. You should find your own style in a lot of things. And even if your style is wrong, a consistently bad style is better than no style at all. And your own style is better than plagiarism when it comes to schoolwork. So again, I encourage you to figure these type of things out. Now I'm going to do this. I'm going to include camera.h. So what we want to do, first thing, we have a camera class. We're going to make a public and private thing. If we look at our application, we have a view and a projection matrix. Now the view matrix is built out of multiple components that you can see here. So we're going to deal with that in a second, but we're going to have two functions, and these are asking, I'm going in the wrong place over and over again. You're going to want to include GLM in here because we're using GLM stuff, glm.hpp, and we're going to have a GLM mat for, actually, there's going to be GLM mat for get view matrix and GLM mat for get projection matrix. And these are important. To position the camera in the world, we're going to need, so if you remember from here, when we created our view matrix, we had this first one, which is the eye position, which is basically the position of the camera. The middle position is where the camera is looking, but we're actually going to do a slightly different way, which is going to be where the camera is. We're going to have a look direction. So from the camera, we're going to cast array. So let me open Paint again so I can describe how this camera works. So from the camera, so assume that this is the camera. So the red point that no, stop it. I said stop it. All right, so here, go into our brushes, the red point in the middle, that must be bigger. That's going to be the camera position. And there's going to be, let's say we're looking, to make it simple, this camera is looking to the right, this way. We're going to define where the camera is looking by adding the camera position plus the look direction, which is the blue arrow. And what this will do is it'll basically give the same thing as we're looking at position 000. But if you take a position and add a direction to it, you're now looking at that direction from the position of the camera, right? So that's going to be the look direction. And then this final one is the up direction, which we're going to use the same thing that we had before, where it is where the up direction is up or positive on the y-axis. So we're going to take these three variables and we're going to create them in our camera class, right? So we're going to say glm vec3, and this is going to be position, glm vec3 look direction, and glm vec3 up direction. Now this could actually, up direction could probably be a constant, but we're going to initialize it as such, 0.f, 1.f, 0.f, so that doesn't change. We can make this a const, but we might need to change it at some point. Look direction, we are going to initialize it with zeros. I think I can just do that. That's just going to put, I think if I just do this, it'll just be zeros anyway. We're going to initialize this one with zeros as well. What now? Now the other half of our camera, if you look here, it was the projection matrix, which defines basically how the view is going to look. So if you give it a 75-degree field of view as we did here, it's going to have a narrower field of view. If you give it 180, you're going to be able to see a much wider amount of the scene in the same view. And then you give it an aspect ratio here. And then you give it the near plane, near clip plane and far clip plane values, which means how close it's going to clip objects and how far it's going to clip objects. So basically, like what range do the objects need to live in order to be drawn by the camera. So we're going to make all of these variables. So we have, and they're going to be. Here we're going to say, so again, it's going to be float of field of view, and we're going to initialize this as 75.f. Now, in this lesson, I'm not going to create all of the getters and setters to override everything. So like field of view, it's going to be initialized at 75, and we're not going to override it in this lesson, but it'll be easy for you to add a setter method that would update this for you. Or if you want to make it public and just make it a pure data class, you can do that as well. I actually think that that's a good practice in a lot of cases, rather than getters and setters, which are kind of bloaty. So we got field of view. We have, what was the other things? It is the aspect ratio. Aspect ratio. Now this is going to not be accurate. This is something we do need to override because it depends on our width and height. So we'll say void set aspect ratio. And this will just be, it'll take a float aspect ratio. And this, we're going to define it inline because fairly straightforward, equal aspect ratio. There we go. So that will that'll make it so we can set the aspect ratio. We might want to include that in the constructor as well. Actually, we absolutely want to include that in the constructor as well. So while we're up here, we're going to make a constructor float aspect ratio. We can make that small like this, and that's all we need for now. The last thing that you're going to need to know is it's not represented here, but you're also going to want to be able to determine whether it's going to be orthographic or perspective. Now, the difference is, if you don't know those terms, and I explained it briefly, I think I did. But so perspective projection, perspective projection goes along the the vanishing point theory of art. So when you draw an object, so let's say you have your square, let's say you want a cube here, right? The vanishing point stuff is as you look off into the distance, objects further away from the camera get smaller. So your cube would end up looking like this, right? Something like this towards the vanishing point, right? And this would be your cube object from this angle. The orthographic perspective doesn't care how far the cube is from the camera. It will always draw the lines at the same distance. So this is good for 2D games. If you're doing a two-dimensional games, this is usually what you'll be in an orthographic perspective. But the same cube drawn orthographic, and this might be hard to do, is going to look like this. All of your lines are going to be straight like this. So you can see the difference. And when we play with it, you're going to be able to see the difference, and this is going to be the difference. One is going to have the vanishing point, and one is going to just be flat like that. So that's going to be the next thing that we're going to need a setting for. So we'll make this bool is perspective, or you can do is orthographic. We're going to default this to true because in any 3D scene, you're going to want it to be perspective. But your assignment requires that you can control this setting. And this is something that we might want to allow as a field as well, is perspective. But what we're actually going to do here is we're going to give it a default value in the constructor. So we don't actually need to provide it every time we build it, because usually you'll want perspective. We'll build out the constructor in a bit. And we're also going to want to be able to set it dynamically. So void set is perspective, bool is perspective. And again, we'll do this inline is perspective equal is perspective. All right. And that's all we need for now. We're going to enhance this in a little bit of a minute here. So we are going to we're going to define these functions. Oh, fine, make it explicit. That's fine. I'm not going to complain about that. We are going to generate all these functions. All right. So the get view matrix is going to be very similar. It's going to be this one here, the look at that we had here. So let's take this and put it in our thing here. Now, so this is creating a matrix is actually fairly expensive. So usually what you kind of want to do is actually you want to cache these values. So let me, I need an include. We need this matrix transform include for this look at function. So we're going to add it here, right? So we're going to, I'll do it inline here, but for performance reasons, I'll show you a slightly more performant way. So this is the camera position. So you can just take the position. As we discussed with the, not this one, this here, as we discussed here, to get the where the camera is looking, you want to take the position and add the look direction. So we're going to simply just put position plus look direction. Now we can just leave this hard-coded, but we did make it basically constant and up direction here. So this is our view matrix. Then we want to create our projection matrix, but we will skip that for a second. We'll go back to the constructor. The constructor is simple. We just want to assign these right over aspect ratio, and is perspective, and this is going to complain probably is perspective. That's odd. I expected that to complain because is perspective is before aspect ratio. So usually they want, I'm going to do it just because it's usually it usually complains. It's a good practice to do it in the order. Value is never used. That's fine. All right. So get projection matrix. Now, same thing that we're going to do here. We're going to take the code here. Now, this will actually change based on whether or not it is perspective. So if is perspective, we're going to return a perspective matrix, and then else we're going to return the orthographic matrix. So let's go inside here, grab here. We will grab our is perspective, or our perspective object here. Oops. And go inside here and add this. All right, so the aspect ratio, the radians here, we put field of view. Here we put aspect ratio, and these near clip and far clip planes are actually things we do want values for as well. But we're going to make them. We're going to define them, but we're not going to change them, and you can add setters for them if you need them. Near clip 0.1f, far clip 100.f. And we can add these here. Near clip, far clip. All right. Now for this one, there's a we want to return this value. So for our orthographic projection, what we also want to do is do the similar function glm ortho. Hey, future me here. After recording this entire lesson, I realized that I actually did, well, I didn't realize, I knew while I was recording it that I did a piss poor job of actually explaining this camera section for orthographic projection of how to set it up properly, mostly because what I was intending to do is different than what really the orthographic camera was meant to accomplish. So I'm going to re-record it now. It's going to feel a little bit awkward in the middle here, but hopefully it'll feel a little bit better. Then I'll try to cut it into the video a little bit smart. So the code you're going to be seeing is going to be a little bit, a lot bit further ahead of where we are currently in this lesson, but the actual camera code itself will make sense here. So let's just go into that now, and let's get that out of the way. All right, so let's go into our camera code. So you see here, now I'm not taking the aspect ratio, and you will get to initial position in a bit, but I'm not taking the aspect ratio here, even though we could, specifically because of this issue, I didn't go back and rewrite it. So instead of set aspect ratio, I have a new set size method here. And that is storing this width and height that gets passed in. And then when we go to our camera.cpp and we get our projection matrix, what we're actually doing is we're calculating the aspect ratio here, just like we were in the perspective matrix here. But we've changed the ortho camera a little bit, and I'll explain exactly what this does. So usually what you would do, so you'll see here, if you look here, it gives you Y minimum left and right, and then top and bottom. So what we're trying to accomplish here, and this is just so that when you switch between perspective and orthographic, that you get roughly the same image as what you're getting with your perspective camera. But usually, so the way ortho works is that you have you're setting up a coordinate system like this. I believe it starts at the top left corner. So I'm going to put it there. But if I'm wrong about that, maybe just double check that information. But I'm pretty sure it starts at the top left corner like this. Yeah. Like this. So what you're saying, sorry. Like this. So what you're saying is with your left and right values, this thing here, you're saying how many pixels on the screen, left and right wise, will be the start and end for your units from the camera, right? So I'm doing, since the aspect ratio is width divided by height, what it's going to do is it's going to take anything from like minus aspect ratio here to plus aspect ratio here. So, which comes out to, so if you look here, it's going to look a little bit different. I'm sorry if I'm not explaining this right. It's kind of, you might want to look it up yourself for a better explanation. So here you see here, is it F11? Yeah. So you see here that what you're getting is you're getting these things in perspective view. And if I can I? All right, so it's going to be tough to see because it's moving along with the camera. Maybe I disable the camera real quick. It's getting some weird lag, but that's okay. So the aspect ratio 16:9 is it's your width divided by your height, right? So what you want to do is you want to go from the left side of it to the right side of it, and then it will be from 1 to 1 here. And that's how you describe an aspect ratio. It's width by height. So your height is by 1. And if you divide width and height, your height will be 1 total. Or it'll be basically 1 total, 1 on each axis. And then your width will be your aspect ratio left and aspect ratio right. So it's kind of weird to explain, but that's what we're doing here. So what you would usually do when you're doing a two-dimensional game is you'd have like your first coordinate here, which would be 0, 0, right? And again, I think it's top left, but maybe just double check that. So your top right would be 0, would be 0, 0 here. And let's say you want your resolution, your pixel resolution to be 800 by 600. So you would define your right value as 800, and you would define your let me just see here. Jerk, come on. Bottom top, yeah. And then you would define your so actually I think it might actually be at the bottom here, but I don't know, you would define your top value as 600. So if you want a 800 by 600 ratio, then that will be how you define it. Now, the reason we're not doing this is because if we do that, and I'll just show you what happens here, is that it makes it so every 1 unit, 800, every 1 unit in engine, which remember our clip space is generally from -1 to 1 type thing, right? Every 1 unit becomes 1 pixel in camera space. So if I do it like this, I think it wants floats. Does it want floats? I don't know. Yeah, it looks like it wanted floats. So when we run that, you're going to see that once we put it to orthographic view, that it's going to make the objects really, really small on the screen. So if I do this, it's so small you can't even see them because it's condensing. So this is from like -1 to 1, right, on the screen. So it's condensing all of this into 1 pixel. So what we would need to do is we would need to make those objects like 800 times bigger, right? So I can probably do that quickly with one of the objects if we want to be able to see it. Where's my object? Scene. So here we'll take this right pyramid and we'll say pyramid right dot transform equal GLM scale pyramid right dot transform GLM vec3, And we'll make this, we'll blow it up by, let's say, 300 times. And we need to do it on all axes. Now, in theory, this should make it at least visible. It should still be, maybe take up half the screen vertically, because it's 300, here it would be 300 pixels high. So see, now you can see that it's huge, but if we do our perspective change, and we're actually, now it's so big that we're too close. So now we need to move. Oh, I think I still have this. So let's move further back. So we'll keep on moving. And now if I hit this, it's still way too big. And you can see why this doesn't do what you want it to do. Can I just change the initial position? Camera, make this 300. That should move the camera back by 300 units. Now I'm too far away. You see that it's coming in and out of the clip plane. So let's make it 150. You can see I improvise all these lessons. Hopefully this edition is gonna, Jesus, still. Oh, I see. So it is 300, but remember our bar clip plane here, that's what this controls. It controls how far you can see before it starts cutting stuff off. So since we're working with really big objects now, we actually really want really big objects like this. And this is also why you're usually not working too much with your z-axis. You're not using 3D objects in orthographic view. All right, here we go. So now you can see if I move up a little bit, I'm moving up a tiny bit. If I go into orthographic view, it's a little bit off because of the way it's set up. So in perspective view, 0, 0 is in the middle. Now if you see, if we move 0, 0, that was in the middle of the pyramid, is now in the bottom left corner. And that's why you see that big shift. But you can see that 1 unit here is roughly 1 unit in orthographic view. That's what I was trying to get at. So when you do your XY coordinates, so now let's change the scale back. Actually, this will probably make it easier. Not this. That's not what I want to change back. Maybe I could have done this in a better way. When you change the scale back here, we'll move this back to where it was. And inside here, we're going to actually make the scale of, it's kind of difficult just because of the way it's set up. But we'll keep the scale on the z-axis the same. And it's still at the 0 point. And let's make it 150. Hopefully that will settle it. No. So now it's right there. If we do this, again, you get it right in the corner. You can see that it gets much smaller, even though we're right next to the object. So we're moving at 1.f, so let's just not move it at all. X-wise. I guess we could not move it Y-wise to get the same idea across, but you're getting the idea. So what I'm trying to do by using the aspect ratio that we did before, and let's just put all this back, is what we had it doing. Was that it was by keeping this all as aspect ratio and using the 1-to-1, what you're doing is you're simulating an orthographic perspective projection from the same point of view that your camera is currently in. So you can see here that wherever I look, it's in orthographic projection, you can see. but it's framing the scene the exact same way the projected perspective camera is. So not this way is not completely useful when you're working with when you're working with 2D graphics. When you want to do pure 2D, you'd want to use probably something else. Like when you're doing UI, you'd probably want to use the proper aspect, the proper pixel density that you need, and then draw those in specific spots on the screen. But as it stands now, you have this, and that's how we're doing it. So that's basically the gist of orthographic projection. Just as a quick recap, just because I'm probably going to cut out a big chunk of how I set all of this up completely. So we have a set size. You could keep this set aspect ratio if you want, or you can change it to size like it's done here. In our projection matrix here, or in our when we're getting the projection matrix and we're creating the ortho, we're going from minus aspect ratio to aspect ratio -1 to 1, near clip and far clip. So it's basically what we have. And when we go to our application, application class, we're setting up, we've set up an initial position, which is a vec3 here. So we have an initial position here inside our constructor, and we also added a, well, we haven't added these yet, so we're going to keep those, but just move camera. But there's an initial position here. And if you look here, that's what I'm doing in application. And we take that camera that we create. We got this initial position basically by doing the same in our application draw call. Where's draw? We had our camera set up here, and there was a initial position. We basically use the same one as that, but you can use the same values I have here, which is 0.502. And then we get our view and projection matrix from our camera, and we upload those to the shader. And that's how we set up the rest of our camera. So that's a little much shorter than what I had recorded before. Hope that was clear enough for you. Sorry for the kind of mix-up. I don't think it happens again in any of the other lessons I've done so far. So let's just get back to the previously recorded thing now. Okay. Now we have everything we need to make our camera work just the way it did before. So in our application, we're actually going to create a camera and keep a reference to it. So we want to include camera here. Camera.h here, and then we want to where do we keep our meshes here. We'll put our camera right above it, so camera, and we'll take camera. That's our camera there. Now we are going to initialize our camera with basic value right actually inside our constructor. So we go to our application constructor. It'll say there's no default member here, so we are going to make this a new line. Come on, stop it. Camera is going to be application name width height. So camera is after all of it. So we put camera at the end, and it will actually have its own line. And this will have its own line too. So camera. What's in our camera constructor again? We have width height, which we will default to 800, 600. Actually, we will default to width, height, and I think that's all we really need. And the initial position, which we can, we'll give as what we had down here. We have this down here. Our initial position is 0, 1, -3. Stop it. Stop it. All right, 0, 1, what? All right, 0, 1, -3, which oh, that's what I did. So I jump between Mac and Windows too often. So sometimes I'm hitting Command key instead of Control. All right. And just to be explicit, we set is perspective to true explicitly, but this is a default, has a default argument, so I don't actually have to provide it. Window title, this is fine. Consider moving it. Whatever, that's fine. Running is always true. That's not true. It's not. Oh, here. We'll change this to continue here, just so that warning goes away. So basically, what this it was saying, and it was correct technically, that since I'm breaking right after setting running to false, it's never actually checking this condition again. So setting it to false actually does nothing. If I continue, it'll set it to false, check the condition, and leave immediately. So yeah, there's a small thing. I don't like seeing like yellow. I try to fix it. Here, it's returning false automatically because we're not doing anything in the update function. But we will be by the end of this lesson. Okay, so now that we have that, we will get our view matrix here. We need to set the look direction, which is currently is 0, 0, 0. So for the sake of making it work right now, so the 0, 0, 0 is nothing. So we want the look direction to be, so what do we have? It's going to be basically, to make it simple, we need to be looking at the opposite way that we're moving. So we're looking at 0 minus 3. We're looking at the z-axis. Here, we basically, I believe, we just want to reverse these. We just want to invert we want to invert our look direction in order to be looking at the origin, basically. Right, so that's basically what we want to do. So for now, what we're going to do, just so we look, we just want to make it look at the origin, just so that we can have it doing what it does before. So for the sake of that, all I'm going to do at this point is here, where not here, in our constructor, where we set the position to initial position. Where's look direction is right after position. So let's make a new line here, just so we can be, and we'll have look direction, and this is going to be -1 times initial position. And what that's going to do, what? 1.f. Okay, it just wants a float. -1 times the initial position. And what this is going to do is it's going to, when you add these together, this plus this, it'll give you 0, which means it'll look at the origin. So it's gonna add up to the same math that we have here, where it's gonna add up to 0, 0, 0. That's what we're doing right now. Okay, so back to here. So we can take our camera get view matrix here, camera dot get view matrix, and camera dot get projection matrix. And another thing we want to do here is in our resize callback, we need to resize. We want to resize the camera, so we're going to take camera dot set size, width, height, like that. And we want to say app camera, because as I explained last time, this function doesn't have access to this, but we set the user pointer to pass in the application so that it has access to all that data, right? So with that done, we should have the exact same scene we had before with the rotating cube, assuming I didn't screw anything up along this process. Yeah, same thing, rotating cube from the same position, right? So now, first thing we want to do is the camera, we always want it to look forward. That's going to be what we want to do at first. So the look direction here is always going to be forward, which is going to be 1 on the z-axis. Now, I think the tutorial gives you -1 on the z-axis, but I don't like using that as a default position. I like to do that. So now if I want to look at the cube, but from the other side in our application, just to start our position, we're going to say 0 like this. And when we say 1, it'll actually be giving us the same view, except not from the top. And there you go. So same view, but just without being angled upwards. Now, if we, let's see, do I still have this? Yeah, so to show off this perspective stuff, we can change this to false. And we can see what this looks like in orthographic view now. So let's go back to where we were before. All right, so now we want to, we're going to do some input handling for now. And then we are going to, we're going to do, well, once we do input handling, we're going to wire our input into our camera to make it so that we can control the camera, which will be useful. So first thing we want to do is in our update function here. So basically every time we loop here, you're going to see that there is a GLFW poll events in update. Poll events here in our draw call here. This should probably actually not be inside draw, and it might actually make actually the swap buffers needs to be inside draw. The poll events should probably be somewhere else. It's got to be inside our update loops somewhere. So let me find where that should be. GLFW poll events. Should it be at the top? I feel like it should be at the top of the update loop. Yeah. Most places I see it, it goes at the top of the update loop. So here, we're going to put it at the top of the update loop so that basically we update all the events. We retrieve all the events that happened in between frames or since the last time we pulled for events, and then we handle everything. So the next thing we want to do is we need to set up some callbacks to handle input. So in here, we have setup scene. We're also going to do in our scene, we're going to also do setup inputs after we open window. So we'll do setup inputs. And we're going to make this a separate function because it might get a little unwieldy. Application class right before setup scene. Here, void setup input. We'll generate that function. We will move it to its appropriate spot in the line right above setup scene. So I like keeping stuff in order manually, but you can do what you want, obviously. All right, so setup inputs. Now, what we need to do here is we need to handle some callbacks, right? There are a few ways to handle inputs, and we're going to do both ways. So you can check for input based on whether something changed if in the input. So when you click a button, you get one event that says key pressed. When you hold down a button, you notice that there's a little gap between the time you hit the button at first and before it starts repeating. You get a event called key repeat every time it repeats the key. Not every time it repeats the key when it starts repeating the key. When you let go of the key, you're going to get an event called GLFW release. Now, most of the time in video games, a lot of your inputs you don't want to handle them only when they change. You want to be able to check them every frame. So there are different ways to do that. We're going to go into the dynamic check every frame way in a minute, but we're going to set up the function that will check the input every frame whenever it changes. So there's a function called GLFW set key callback here that takes as a parameter your window, and it takes a callback function. So again, I like to use Lambda, so we're going to do this way. And now if you want to know the shape of the key callback, Go here, glfw key function. Come on. Now I'm pretty sure it's going to have like, it's going to be, here it is. It's going to be this. So you can literally just take this function here and pass that in as your parameters there. And you'll see that that worked as like it's supposed to. Now, where did we, before we do that, we set the application user pointer here, which is good. All right. It happens before it gets to set up inputs. So we're probably going to need a reference to our app. So we're going to say glfw get window user pointer on window like this. And we are going to, oops, not underscore window, and we are going to reinterpret cast that to a application pointer like we did before. So we're going to need that, and we're going to actually need that probably in every one of these functions that we make. So you're going to see here we will get the key, we are going to get the scan code, and we're going to get the action. So what we're going to do, we're at first we're going to make it so that if we ever receive the escape command, then we will get. So we'll say if key equals glfw escape key escape, we're going to quit the application. So we're going to say and if it's press. So if I think it's scan code we want. Equal glfw press, then we will say app running is false. And what that will do is that should make it so that when we hit escape, it will close the window. Yeah, it closes the window when you hit escape, just like that. You probably heard me click the button. So I'm going to put this back in perspective because I don't want it to be in orthographic right now. And I'm just going to test that to make sure it's working as intended. So you see here, it opened perspective. When I hit escape, we get the glfw press event and it closes the window. Okay. Now, once that window is closed, we're going to do, is there anything else we need to do with this type of event? So you can do this with all the keys. You can find the list of keys just by typing glfw. So where's my setup inputs? Just by looking at like glfw key, and you can see all the list of keys here. In most editors, you can use Control click or Command click on Mac to actually just go look at the list of keys in order here. Now, what you'll usually do is you won't usually do this in an if statement. You'll probably use a switch statement on key. And this will be a case here. It'll be case like this. Like that. The colon goes after the case. And go here, and you want to break out of here. And you can just make a default at the bottom to shut it up. To shut up the yellow, or that should be it. Yeah, okay. It says it would be better as an if-else statement, but that's because there's only one case. If there's a whole bunch of different cases, then this will be better. But we'll do this. That's our key callback. We do a very similar thing for mouse callback. Now, what you can do, this function can get very long if you do it all in lambdas like this. But what you can do with the app pointer is that you can define on your application class. We're going to do this with the mouse callback specifically. Cursor. Yeah, so we're gonna do a mouse position callback here. So basically, okay. So let me take a step back. So when you set these, it's going to call this function whenever a key changes. You can do the same thing with your mouse object and your mouse buttons, your mouse position, and your mouse scroll, except you might also want to make this into its own function in your class versus a function directly versus a lambda. I often prefer lambdas because usually these things are going to be fairly small. You'll have different ways to handle other things, but if you prefer the other way, since we're using everything as a class, and I don't like naked functions on the global namespace, which basically means that everything is namespace under application here. So if I wanted to pass, here, let me create the function so I can show you what I mean. So let's say we want the mouse position, we can do set mouse set cursor position callback. Yeah, that's it. Again, window, and this one is going to have, we can go through, but I have it on my other window here. It's going to have a function list of this. So this is going to be the mouse cursor callback. It's going to require these functions. Now, if you want it to be a function on your application, so we can make it private. It doesn't need to be public. You would do something like void mouse position callback, and this is going to be lowercase, and it's going to have those inside, and we're going to generate that thing here. And now we want to use that in the function. So usually when you pass a function, you're going to do something like this. This is what you would want to do in a new or C++ application mouse position callback like this, but you'll notice it doesn't work because this resolves the same thing as if we had done, sorry, I can control C. If we had done this, we put this capture keyword inside, it resolves to a very similar thing. And to be able to do this, to pass in a function, your functions actually need to be static like this, void mouse callback. And this is just an example. I'm going to delete this like this. And then you can pass in just mouse callback like this, mouse callback. And this would work. But we generally want to avoid making random static functions living on the global scope that have no insight into the different objects that are being where it's being called from. Now here it's a little bit of a different story because this GLFW window here has the context. It has this app object inside, but we're going to leverage this app object so that we actually don't need to make it static. We don't need the GLFW window in here because by the time it's called, it will know its own context. So we can remove that in our .h as well to make the squiggles go away and to make it work. And then instead of doing this, we can go back to, should have reverted it before. So GLFW window, and then these like this. And then we get our app from our user pointer. And then now we can call app mouse position callback just with the X position and the Y position like this. Right? So this makes it a little bit more concise, but it also means that this will have full access to everything and you can have everything nicely organized and not have to screw around with everything. So that's how you control stuff. We have very similar things, and I'm going to do everything actually in as lambdas for now, except for this one because we already put it there. But I'm going to have everything as lambdas for the rest of it. So there's set cursor position callback, so it'll give you the new mouse position every time the mouse moves on the screen, which is more generally, I believe, more efficient than if you had were updating it every frame, checking every frame. I think it's more performant, but it might also be slower. So you might want to test stuff around. The next one is going to be the scrolling callback. So set scroll callback. Again, it's going to set you can pass window. And this one, you're going to have a lambda that has GLFW window, double X offset, offset, and double Y offset, like this. Now, I'm not entirely sure what X offset is. I think I kind of want to say that this is in case your scroll wheel supports left and right movement. So maybe if you have a trackball, this might support trackballs. But let's just put this again. The sample code that I'm stealing this from, the tutorial, is using namespace std, and I don't like that. So we're going to see what this gives us just as an experiment because I'm curious. I believe X offset is not going to change. Yeah, X offset doesn't change, but Y offset does. So basically, if your mouse for whatever reason supported left and right scrolling, which I know some do, but mine doesn't, and most people's won't, your X offset might be different. So, but that's how this works. And then finally, mouse button callback, GLFW mouse button callback, set mouse button callback. Again, window, GLFW window, like always. Then it would be window, and then it would be, what are the arguments for this one? You're similar int button, int action, int mods. Now, I find that, what is scan code? So, wait, should this be action? I mean, it worked, but where's the, oh, did I, all right. That should be here, and remove this one. All right, and a semicolon. So we're gonna play that. What's the time at on this? Oh man, this has been going for a while. All right, we're getting there though. Escape. All right, so that works too. So I'm going to assume that this is supposed to be action. Scan code is another way to figure out what key it is, I believe. Sorry about that misinformation. For some reason it worked though. So I don't know. Yeah, I don't know why this worked with either action or scan code, but I'm going by the mouse callback. This needs to be action. So when we're in our mouse callback, this is going to be fairly simple. Give me a second. We're getting close to the end of everything. Right mouse button pressed, right mouse button released. So similar, we're going to put a switch statement inside here. Switch button on here. Now what I'm going to do this using generation. Come on, give it to me. Fine. We're going to say case GLFW mouse button left. And I like putting curly braces here because of reasons. GLFW mouse button middle. Case GLFW mouse button right. And then a default case. We'll just say std_count unhandled mouse button events. And put an end line there. All right. So now you can just check whether or not it's released or not. So you can say if action equal GLFW press. So the mouse does not have a repeat state or action. So it's either going to be pressed or GLFW release. It's going to be one of the two. So it's all going to be one of those ones. Now I'm not going to put anything in there. You can trust me that it works. Here, let me just put. I don't want to waste too much time. Mouse button left press. Now I'm just going to do that. Just so you can see that yes, it is working. When I click, it should give me my mouse button left pressed like that. You see it's showing up when I click, mouse button left pressed like that. So just remember that this is basically what it's doing. So with that done, let's set it so that we can control the camera with our keyboard. The simplest way to do it, we're going to do WASD first, okay? So we're going to do, in here, we're going to put handle input here, which then will require a thing here. So in update, we can put it right above here, handle input, like that, generate it, move it to above where it is declared in the header. Now our input is going to be simple. We're going to check for WASD, and if any of it is pressed, we are going to we're going to move the camera. So to move the camera, all we need to do is we're going to need to, let's just say, we're going to say void move camera, right? And this is going to take, I'm going to put move direction here. And we're going to say direction, and we're going to put a float move amount here. Now move direction, you can do this with vec3 if you wanted to make it a little bit more, you can use this with the vec3 to define which direction you want to go, but by using move direction you can make it a lot more explicit. So in your public, we're going to actually make an enum class here, move direction, and this enum class is going to have forward, backward, left, right. So that will mean that we can, come on, generate it, be cool, come on. Fine, I'll do it myself. Rare that this happens in CLion, but I'll do it myself. We'll go into camera.cpp, do that here, move camera, move direction, and then we say camera like this. Okay. So we can make a switch case here, and we will say direction. And now it'll say create the missing switch cases. It'll generate that for us. And like I said, I always... So we're going to make a GLM vec3 move direction like this, and we will set what that's going to be in all of our cases. And then once we're done setting our move direction, we will update our position. So it'd be position is equal to plus equal to move direction times move amount, like that. So what this is going to do is that it's going to pick a forward direction, or pick the direction the camera is moving, and it's going to add us a percentage of that direction to the position to move the camera. And this is just using vector math to, let's delete this. So if you have a position here and you want to move this way, then you just need to add this vector to this position, and then you get a new point at the new position, right? So that's how that works. So our move forward, that means that we want to move forward in the direction the camera is facing. So we already have the move direction for this. This will be move direction is equal to look direction. When we're moving backwards, it's going to be the same thing, but it's going to be minus look direction equal minus, God dang it, look direction, like this. So that'll be forward and backward. Left and right is a little bit different. So when you want to move left and right, if you're here, and you have the forward direction, which we'll do in blue, So we're known value blue. We also blue, and then we have the up direction of the camera, which is going to be in red, let's say. So we know where it's looking, and we know where the up direction is. To find the right vector, we need to find a vector that we'll mark in pink that is perpendicular to both these directions, like this. And now if you remember your math, to find the a vector perpendicular to two other vectors, you take the cross product. So that's what we're going to do here. And we also want to normalize that cross product. So because our look direction should be normalized as well. So our left is going to be so depending on the order and the way everything does, I don't know whether or not it's going to be positive or negative, but we'll play with it and we'll see what works. And if it doesn't work, we'll just invert the signs. So here it'll be move direction is equal to GLM normalize GLM cross, and it'll be front camera look direction, and then up direction, like that. And then the move direction going right will be the opposite sign of this. So we'll just stick a big old negative in front of it, and then we've got our move camera function working. So going back to our update handle input function, what we're going to do is we're going to introduce a new function that I was going to get into to check whether or not a key is pressed every frame. We use glfw get key like this. We pass in the window and we pass in which key we're interested in, key W, like this. So this is our W key. So we can just do this in our if glfw key like this, and then we can just say move the camera dot move camera move it'll be camera move direction forward, and the amount we'll deal with that in a second. Move amount like this. All right, so there's a couple concepts here. Our camera will need a move speed, which won't live inside here because the camera object is different than the camera concept. So we'll put in our application here, we'll say camera, we'll just call this move speed actually. So we'll say float, move speed, and I'm just going to make it 5, right? And we'll use the initializer here, move speed 5. So that's going to be our move speed. Now, usually you're going to have a delta time here to regulate your frames to make sure that on a really fast computer, this isn't just going to zip along. But what we're going to do is, for now, we're going to say const delta time is going to be, we're going to assume that it's going really, really fast. So it's just going to, we're just going to put 0.001f for now, and what we can auto. And we can adjust that as we need to, and if we get to the point where we're dealing with delta time, which the tutorial mentions, but I don't know if it's actually mentioned in any other tutorials. I'll have to look through, but we can do that in a minute. But then we can say auto move amount is equal to move speed times delta time. So delta time as a concept is how many seconds between frames has passed since the last time you updated your this function was called. And the reason that we use that is because if you're on a really fast computer and you're not limiting your frames artificially, you could be running at 1,000 frames per second, which means move speed will be ridiculously fast. Or you could be running at 3 frames per second, which would mean that move speed is really low. So just to test this concept to make sure that it's working as intended, we'll hit play. And now if you see if I hit W, it zipped along. So we'll add another 0 to this because it's a little bit too fast. you can see that as I held W there, my camera zipped along and moved forward. There we go. It's a little bit slower now. All right, now we do the same thing with all the other keys. So we're just going to put WASD movement inside here, like that, and WASD. Now this is the move speed. So A is left. So we're going to move this here. So we'll put left here. S is backward, and D is right. And this will be more intuitive than just using negatives, I think. So that's what we're going to do. I know I just rethought it like 3 times, but you can see that there's many approaches to creating an interface. I'm just checking everything's still working as intended. And now we give a single move amount, but we say which direction it goes in. And if for whatever reason we want to go negative, then we can do negative. When you get to gamepad, that's where this is going to come into handy, being able to pass in a negative value, because usually you're going to get your axis value, multiply it by your move speed and delta time, and just pass that straight into your forward axis. But with WASD, this kind of makes sense. So we'll leave it like that. So let's move forward on to what we are attempting to do. This one is not what we need. This one is not what we need. All right, this is a tutorial we were working on. It's really funny. This is the first time I look at the tutorial, and it's the first time I realized that at some point they made a multicolored cube very similar to what I did. So interesting. So the next thing we are going to do is we are going to they do talk about delta time here, so we'll do that at some point. So we want to be able to move the mouse. So we want to be able to move the mouse and change which direction we are looking at, right? So so to calculate, to be able to rotate the camera itself, we need to be able to, we want to be able to specify the yaw and pitch of the camera, right? So usually you would do a lot of this by doing stuff directly with the transformation matrix. You would take a matrix and you would translate it, rotate it, and stuff like that, and then do that. We're going to do it the way Learn OpenGL does it, just because I don't feel like going through the math. The math is actually kind of easier doing it with matrices, but we're going to do it their way, just because we've already got a lot of stuff here. So we need some more values in our camera class. We need yaw, pitch, and roll, which are going to be floats, which are going to be yaw, float, pitch, and float, roll. We don't need roll. You could do roll, but we don't need to, because roll is not supported by the way we're doing it. So what we're going to do is we're going to add a new method called rotate. Rotate by, and then this is going to take 2 floats, one yaw and float roll, right? And that's what we're going to do. We're going to wait until C-line catches up, because whatever, I'll just write it down. Float, yaw, float, pitch, yaw, pitch. And did I put roll in the other one? After eating, my brain's a little fuzzy. Yaw and pitch. And did I put rotate by? I did put rotate by. Okay, so we got yaw and pitch here. So this is going to be fairly simple. All we're going to do is do a yaw plus equal yaw, and pitch plus equal pitch. Now, so when you're looking at a first-person camera like we're putting inside this application, you're going to want to, so the yaw is the up-down movement, and the pitch is the left-right movement. I should have said that. So you want to be able, no, other way around. The yaw is the left-right movement. The pitch is the up-down movement. Sorry. You start running into issues if you start doing calculations based on a pitch that's higher or lower than 90 degrees, or higher than 90 degrees, or lower than negative 90 degrees. It'll like flip your camera upside down, and your different things will look wrong. We're going to use a function that does this properly. We're going to std clamp, and this here, and I think this is in the math header. Let me just include math. It might be algorithm. It actually is probably algorithm. Algorithm. Std clamp. Yeah, it was in std clamp. So we're going to give it the pitch, and we're going to say it's going to clamp it to between 89 degrees and 89 degrees, like that. Like that. Come on. And then we assign that to pitch. So what that's going to do, it's going to clamp the values to between these two. So if it's below, it's going to make it the minimum. If it's above, it'll become the maximum. And then once that's done, we're going to call a function that we're going to create. It's going to be called recalculate vectors. So basically what this is a function that every time you rotate, you have your yaw, pitch, and roll, right? When you rotate your camera, your front vector is going to be different, and your up vector is going to be different as well, right? So, because when you look up, when you rotate looking upwards here, let me use good old paint again. That'll make it easier. Okay, come on. All right, so you have your camera that's looking this way, right? This is your forward vector in pink, and your up vector. And your up vector is going to be in whatever, green, like this. If you rotate your pitch or yaw, whenever you rotate in general, like let's say you want to rotate like this, right? You rotate this way, then your front vector will become like this, and your up vector will become like this. So clearly you can see that our view has changed, and we calculate our view based on these vectors. So the recalculate vectors, what it'll do is every time we rotate our camera by any amount, we're going to recalculate the vectors so that when we go here to get our view matrix that takes our look direction and up direction, that those two values are correct. So inside our camera here, we're going to make a private function. Void recalculate vectors, like this, and this is going to have some math. Let me see if I can find the place where it explains this math here. So I'm not going to explain all the math, because I mean if I sat down and read it, I'm sure it would make sense. It's a trigonometry stuff basically, but basically it's calculating using the yaw and pitch here. You can figure out that what is the pitch and what's the yaw and stuff like that, because the pitch is an angle, right? And the cosine of pitch is this, and the sine of pitch is this, and you know that the x direction of your camera is going to be the cosine times this. It's going to be a combination of these two vectors, or of these two, whatever. I would need to read it, but it's here. If you want to understand how this math works. So this is what I was saying. Pitch is up-down movement. Yaw is left-right. Roll is something that we're not supporting in our camera, but it's left-right, or like doing a barrel roll. So trigonometry does this, and this is basically where we get to our recalculate vectors type thing. So with that in mind, what you're going to do is first we need to recalculate the front vector. GLM, and the front vector is our look direction. So we can say our look direction is equal to GLM normalized, because the look direction needs to be normalized, and it'll be GLM vec3, and this vec3 will have as our .x component. Oh wait, we want to use the initializer like this, which will allow me to use this notation. .x is equal to what we're just looking at, cosine. Okay. Cosine of GLM radians of our yaw times the cosine of our GLM radians of our pitch. Now, what is this complaining about? X dot y equal 1.f. B equal 1.f. Now, what's this complaining about? No matching constructor. Oh, these are giving doubles probably, right? Cast float. Yeah. No, that's still. Why is this not? No matching constructor. Do I need to just do it like this then? Yeah, okay, so let's just do it like this. I was trying to get fancy with C++20 stuff, but apparently it doesn't want to do that. So we take the cosine of our yaw times the cosine of our pitch, and that gives us our x direction. So our y direction is going to be the sine of our pitch, and then our z direction is going to be the sine of our yaw times the cosine, right? Yeah, cosine of radians pitch. So this is our look direction that's normalized, and then to get the no, we don't need the right direction. So we do need the right direction. So we need to calculate a right direction action, which is going to be the make that auto, which is going to be the normalized result of a cross product between this front vector that we just calculated, so our look direction, and the world up direction, which is basically a constant, which is basically the 0, 1, 0 constant. That's our world up direction. And then we can store the up direction now, which is the up direction, which is again the normalized result of the cross product between this calculated right direction and our look direction, front vector. So what this does, and why is this no viable overloaded? This argument has type const GLM vec3, but because we marked the up direction as const, which was a poor decision. Again, I make mistakes. I've been recording these for a few days, and yeah. Anyway, so that's how we do it. So what's basically happening here is the normal. So we have this new, let's say this new rotation, right? And the world up vector is always pointed this way. World up is always basically pointed straight up like this. So what we're doing is we're finding the, and assume that, let's say purple is what the right vector that on this original one. So to find the right vector of this one, we're actually going to just take a cross here, which is going to make an object perpendicular to both this one and this one. So this is basically just taking a random vector and getting a perpendicular vector. So this one is perpendicular to this one. These two are perpendicular to each other. And well, technically they're all perpendicular to each other. And by using these two vectors now, we can calculate this new up vector by getting the new the vector that is now perpendicular to these two front and right vectors that we just calculated. So it's kind of a roundabout way of getting our up direction, and then we can use our up direction to do our view matrix and all of that as well. All right, so that is how you do that. This is recalculating vectors. Now that's pretty much all we need for that. Now we can just do the actual mouse stuff. So what do we need to do? So to handle the mouse, we need to determine how much the mouse has moved since the last time we got a mouse position. So what we will do is we need to keep two new variables in here. So it'll be double last, and you know what? We're not actually going to even. Yeah, I'm going to do it this way. So what I'm going to do is we're actually going to store this in a glm vec2 last mouse position. And I do this specifically just to have them both together, and we have an X and a Y, and it just reads better than having last mouse X, last mouse Y. So what we need to do, yeah, we should probably do that as well. We won't do it for now, and then we'll fix the issue when it comes up, because it will come up. So the X offset, we need to calculate the offset, or how much the mouse has moved since the last position, right? So we're going to say float last mouse move X. Actually, we're just going to also make this a vec2 mouse offset, or we'll just say move amount here. And this will be, it will be the X position minus the last mouse position dot X. And it'll be the Y position minus the last mouse position dot Y. And then once we do that, and now this I believe might need to be reversed, but we'll get there if we need to. So then we have to set the new last mouse position dot X is equal to X position, last mouse position dot Y equal Y position. And then in here we will do so the camera itself. So I'm keeping all the camera stuff separate from all of the like movement stuff, like input, like all the input variables. So what we're actually going to do is we're going to have another thing here, another vec2, which is going to be a camera look speed, like this. And now camera look speed, this will be another thing that we can set inside our constructor. Just like kind of like what we did with our camera here, we set a bunch of stuff manually. We can do that here as well. Camera look speed. Did I not put underscore on that? I didn't. Okay, the camera look speed. Now I don't know how much they use for camera look speed before, but let's just say it's probably something that we want a little bit. So X and Y, on the X axis, we want to look fairly quickly. So let's put that at 10. And the Y we'll put as, what do we want to put the Y as? Well, let's put it as like 3/4 of that. Like that. Is that good? Like that. Okay. I just removed that last comma. We have a bunch of random warnings in here. Case. Oh, because they're empty. That's why. That's fine. We might not end up using this mouse. No, we will end up using this. Will we? We might not end up using this mouse button callback, but we'll see. And then here, though, now that we have last mouse position, we do the same thing as Right. So actually, I don't think we need to do anything else with this. I think we can just then call camera dot rotate by, and we say last mouse position dot x, last mouse position dot y. Now we could have passed that in as a vec too, but I think it's worked. All right. So now in theory, we should have roughly a good amount of what were those errors? So what's happening, and this is what I said we might need to fix. When we initialize, I think what's happening anyway, when we initialize our, where is it? Our last mouse position, these default to 0, right? So what we're going to do is we're actually going to initialize these as -1, -1. And because actually it might come out as a negative. So, and this doesn't have an underscore. I'm going to rename this and add an underscore to it because it needs to have an underscore on it because it's a private member variable. We're going to fix this the same way they did on Learn OpenGL, though I feel like there's a better solution. We're going to say first mouse that is initialized to false. And inside here, when we do our handle mouse movement callback, we check to see if first mouse, or if not first mouse, then we say last mouse position dot x equal basically this. Basically do this. And we set first mouse true. That should, yeah, so that should fix the issue. Like, oh, and I'm probably, yeah. Sensitivity. So the mouse sensitivity is probably all screwed up too. Sensitivity. Which is this one. I'm just trying to see what what sensitivity they set. Sensitivity 0.1. Okay. So another problem is that, so I set these camera move speed stuff here. At the top here, I set my sensitivity to 10 and 7.5. This should be much smaller. So I was expecting to multiply this by a delta time type thing, but this I was wrong. This is not how you. That's not how you do it with the callbacks. So still. Oh. All right, I'm dumb. This should be move amount, not last mouse position. I think that's the issue. So basically, we were putting like 600 or whatever in there because it was. Now it's still doing nonsense. So what's going on now? Oh, and then finally, we also need to do times mouse sensitivity. I'm having mouse speed. What do we call it? Why am I having so much trouble today? Move speed, camera look speed, that's what I called it. Dot X. Come on. Dot Y. Okay, let's try that again. Don't worry, I believe. Just gotta believe. Still being freaking dumb. Oh. So here we would, in here we need to recalculate the vectors. Recalculate vectors inside here. What is look direction by default? Yeah, front 0, 0, -1. Oh, I found it. Okay. So it is. All right. So it is moving the almost correct direction. It's because the initial position, I guess, is wrong. So we want the look direction to be forward. We want the application to have an initial spot of what, 3? Yeah, okay. And then in our camera, we have in here, we have our pitch starting at -90. All right, so that's because, yeah, okay, that should be right. All right, okay, so a couple more things. Our sensitivity here, way too low. I mean, there we go. That's better. Now, another thing is that here, when we calculate our mouse move for Y, it's currently inverted. So we can actually just do this. Put the Y position. Now, when we move up, it should go up. When we go down, it should go down. There we go. Down, up, down, up. And I still don't like that sensitivity. So you're gonna want to play with these numbers a little bit. But another thing that we want to do as well is this function here, which is going to be mouse position callback. We're going to actually call it from our update function in our handle input, and we're going to do this. We're going to glfw get mouse position, mouse position. Get cursor position like this. It'll be window, and it'll be a reference to X position and reference to Y position, and it will be int X position, Y position, this, and these are probably supposed to be doubles, so let's make these doubles, and then we will call our mouse position callback using X position and Y position. Now, why do we do this? Is because, so if you notice, we're getting the cursor position, but it only did anything if we were on the window itself. So we're going to, where we have set up inputs, where we create our mouse callback, we're going to actually disable this callback. And now, when you start the application, it's going to always look for where your mouse is, like this. And you'll see now, no matter where I am on the screen, it works. And okay, whatever I had pasted in had screwed it up. God damn it. Oh God, sometimes I don't understand what's happening. All right, so now finally we want to do the zoom. So the way we did zoom, so what we're going to do, and this should be one of the last things we want to do in this video, I think. I'll look at the curriculum, but we need a new one more value, float zoom here. We'll start it at 75 f, a decent field of view. We're going to say void increment zoom like this, and float amount, and this is going to be float amount, and this is simply going to say float plus equal amount, or float zoom plus equal amount, and then we are going to clamp this between 1 and let's say 75. We'll start here, and zoom like this. Now, what we will do is we will, inside our application, we go to where we're handling our scroll wheel, and this should be pretty easy. Basically, if it's down, it's a negative number, so we will get our app like this, and then we will call app camera dot increment zoom, and we'll just say y offset, make it real simple. And now if we hit play, when we scroll our wheel, it is not working. Nice. Because why? So that this is working correctly for field of view. Oh, all right. So all we're going to do is, and this is actually going to be, instead of zoom, we're going to change this to field of view, and we actually don't need a new variable at all. Field of view, and we'll get rid of that extra variable that we no longer need. All right. So I just never actually wired it up. I'm clearly on the more on the tired side today, making lots of mistakes. So now zoom in, zoom out. Now it looks like we want to invert that value. So when we zoom inside here, actually no, we're going to invert it inside here, because when you do +1, you would expect it to zoom in. So by going by the contract that we're creating, that would make sense. What we do want to change here is when we call increment zoom, we're actually just going to ×2 this, just to zoom in a little bit faster. Now zoom out, zoom in, zoom out, zoom in, zoom out, zoom in. Yeah, there we go. And there we go. Now we have zooming and all of that. What else? There was delta time in here. So delta time is relatively simple. What we will do is at the beginning, we'll look into our update function. So at the beginning of our update function, actually in the beginning here, while running, we are going to call float current time is equal to glfw get time. Now we also want to have a new float in here called float last frame time. Last frame time. We'll initialize this to -1.f. Now in here, we will do if last frame time is equal to -1.f, then last frame time equal to current time, and then auto delta time is equal to current time minus last frame time, and last frame time equal to current time, like that. And then we will pass our delta time into our update function like this. So we'll need to go look at our definition of update. And we'll need a delta time. And we'll also need a delta time inside of our handle input function like this. And then when we go back to our application.cpp, we'll add this here. We'll pass this in here. And in our handle input, we want put float delta time and get rid of this value here. Now everything should work roughly the same, except now everything's going to be moving slower, realistically. No, actually, everything is moving roughly the same, but now it's all taking into account how long everything is taking. So the movement speed is now going to be in seconds. So it'll be, I guess, 5 units per second. The camera look speed isn't really affected. I'm going to increase this again, by the way. And that's our delta time dealt with. So that's going to make it so that if you send this to a friend and he has a slower computer to you or a way faster computer than you, it should run relatively the same no matter what. And what we're going to do, we won't do that. Now, what else? Right, we're going to do one more thing. This is just to demonstrate some interesting stuff. So on our key callbacks here, we have one for whether the app is running. We're going to make one more case here, case DLFW key. We're going to say F11 is the one I'm going to choose. If action is equal to DLFW press, then app camera set is perspective to not app camera dot is perspective, like this. And we need to add that function. So in our camera class, we will have right here set. We're going to add the getter bool is perspective, return is perspective, like this. And what's this say? Can be made const. That's actually I was thinking the same thing. All right, so now that should have gotten rid of the red there. Now when we hit F11, what? Oh no, what's it? Oh, I forgot the semicolon. I forgot a semicolon. All right, so now that that's done, we should be able to switch between, there we go. So you've got your orthographic view here, and you'll notice I can rotate, I can look around the scene, but if you can hear me, I'm using WASD. So look, damn it, where'd it go? Dang it, dang it, dang it. All right, let me reset that. So you can see I can move around the scene, but even though you can listen, if I press WASD, actually you can see the clip plane, that the size never changes no matter what. So if I go back here, I can go really far away and it gets smaller and smaller. I press F11 to go to orthographic, boom, it's in the same size until you get the past your far clip plane. So you can see still getting smaller. Oh, still getting smaller. And eventually it'll disappear because it'll be past the 100 unit bar clip plane. Other than that, that is everything you need to know to get through week 4. I apologize for it being a little bit less straightforward, I want to say, this time than it was the last few. My brain is not working as well today, and I am mostly making a lot of this up as I go along, because I want you to see how I think through problems, and also, seeing the mistakes being made is also not a bad thing to see as well. So, all right. So I hope you didn't mind that longer, little bit more hectic way of getting through the material this week. Next week, what we're going to do is we're actually going to look at texturing. I think that's pretty much everything that you need to do for next week is know how to texture stuff. So let me see. Yeah, so basically we're gonna have to learn the texture stuff specifically, so that you're gonna have to make a choice between either tiling your texture on your object or putting 2 textures on top of each other. 2 textures on top of each other is actually kind of interesting to talk about, because it requires a little bit of you have to set some variables and stuff like that. So we'll look into that. Texturing shouldn't be too much work. Most of it is going to be loading the texture file into memory, and then once you've got the texture file loaded into memory, it's really shader work and a little bit of adding to our mesh class. So hopefully it'll work out okay. Everything will be good. But that's what we're going to work on next week. So thanks for tuning in, and tune in next time for week 5. And remember, join our Discord. I'm there. More people who have gone through this course are there, and we're a great community. We're probably one of the biggest CS communities around. So see ya.